You know that brain inside your computer, the CPU? It's an absolute speed demon, doing billions of things every single second. But have you ever stopped to think about how that lightning-fast chip actually talks to all the slower stuff? Your keyboard, your hard drive, even your printer. It's a huge communication challenge. And today, we're going to see exactly how it was solved.
Right, so this is the real question, isn't it? How does one single processor, which is just flying along at billions of cycles per second, manage this whole universe of devices that are all running at different and much slower speeds without grinding the whole system to a halt? It seems like a recipe for total chaos, but the solution, as you'll see, is surprisingly elegant. So here's how we're going to break it down. First, we'll look at the fundamental speed problem. Then, we'll dive into the clever solution of delegation. After that, we'll explore the actual language computers use to talk to each other, which leads us to a chaotic time in history when nothing was compatible. And finally, we'll see the modern system that makes everything just work.
Okay, so the first big hurdle we have to get over is this massive speed mismatch. Your CPU lives in a world of nanoseconds. It's just mind-bogglingly fast. But the physical world, where things like motors and printheads have to move, that world is incredibly slow by comparison. This is the core conflict we need a solution for. Just think about the scale of this for a second. A CPU can perform billions of operations in the time it takes a printer to mechanically roll one single sheet of paper past a printhead. It's not even close. If the CPU had to personally sit there and manage every tiny movement, it would be a colossal, almost criminal, waste of its power.
And look, this isn't just about something complicated like a printer. Even early keyboards were a huge problem. The CPU itself had to constantly check a grid of wires over and over and over again just to see if you'd finally pressed a key. It's like forcing the smartest person in the world to do the most boring, repetitive job imaginable. There just had to be a better way.
And that's where the smart solution comes in, delegation. You wouldn't have the CEO of a company personally answering the phones and making coffee, right? Of course not. You hire specialists for each job. Well, in the world of computing, that specialist is called a device controller.
Pretty much every single thing you plug into your computer has its own little brain. If you've ever seen that little green circuit board on the back of a hard drive, that's what you're looking at. It's device controller. Its one and only job is to be an expert on running that hard drive so the main CPU doesn't have to be.
So the process itself is actually super simple and incredibly efficient. The CPU just acts like a manager. It sends a high-level command, something like, "Hey, hard drive controller, go find this file for me." And then, and this is the important part, it immediately forgets about it and moves on to other important tasks. The controller handles all the nitty-gritty details, and when it's done, it just taps the CPU on the shoulder to let it know the job is finished. Okay, great. So we've delegated the work, but that just creates a new problem, right? How do the CPU and all these little specialist controllers actually talk to each other? What's the language they speak? And what are the rules of engagement? Well, one way to do it, and it's probably the most common, is something called memory mapped I/O. The idea here is actually pretty simple. The system just pretends that a device's control registers are just another part of the computer's main memory. This is brilliant because it means the CPU doesn't need to learn any new tricks. It just uses the same old load and store commands it uses for everything else. Now, the other way to do this is with what's called isolated I/O. Here, you basically build a whole separate communication highway just for the devices. This is great because it means the traffic for memory and the traffic for devices never get in each other's way. But there's a catch. The CPU now needs special on-ramps and off-ramps, these new in and out instructions, just for this special highway, which makes the CPU itself more complex. And when you put them side by side, you can really see the trade-offs. Memory mapped I/O keeps the CPUs simple and elegant, which is a big reason why architectures like ARM, the chips in all our phones, use it. Isolated I/O, on the other hand, adds complexity to the CPU in exchange for that clean separation. And then you have the x86 architecture, the one in most PCs, which is just complex enough to say, why not both? And supports both methods. All right, so they know how to talk, but what about when to talk? Remember, the CPU gave an order, but the device is slow. How on earth does the super-fast CPU know when the slowpoke device is actually done with its job? The first and kind of clumsy way is called polling. And honestly, it's the computing version of a little kid in the backseat of a car on a long road trip. The CPU has to stop everything it's doing, turn to the device, and ask, "Are we there yet?" The device says no. So the CPU does a little work, then asks again, "Are we there yet?" It's just a massive waste of the CPU's precious time.
But there's a much, much better way. Interrupts. Instead of the CPU constantly nagging the device gets to be proactive. When its task is complete, it sends a signal, an interrupt, that basically taps the CPU on the shoulder and says, "Excuse me, I've got that thing you asked for." This is the magic that lets your computer feel so responsive, because the CPU can focus on your user interface until the moment it's interrupted with new data. So, now that we have all the pieces on the board, let's take a little trip back in time to the Wild West of personal computing. This story is the perfect example of what happens when you get all this communication stuff wrong. So get this. Back in 1977, two legendary computers came out, the Apple II and the Commodore PET. And here's the crazy part. They used the exact same brain, the MOS 6052 processor. You could literally take the chip out of one and put it in the other, and it would work. And yet, if you tried to run Apple software on a Commodore, it would be complete and utter gibberish. Why? The problem was, it was total chaos. Even though they both used that memory-mapped I/O idea we talked about, each company just made up their own map from scratch. They hardwired the video card, the keyboard, everything to totally different memory addresses. So a command that meant draw a blue dot on an Apple II might accidentally tell the Commodore PET to erase a chunk of its own memory. It was an absolute nightmare. Yeah, this couldn't last. The industry absolutely had to find a way to create some order out of all this chaos. The solution they came up with is the elegant hybrid system that powers pretty much every computer you use today. It combines that simple software view with powerful standardized hardware underneath. So, for a long, long time, motherboards had this two-chip setup. The CPU would talk to a really fast chip called the Northbridge, which was like a high-speed traffic cop for the most important stuff, like system memory. That Northbridge would then talk to a slower Southbridge chip, which handled all the other input and output ports. The problem was, this whole setup created a major performance bottleneck right in the middle. So, what was the modern solution? Well, it was pretty straightforward. Just get rid of the middleman. Today, all those important jobs the Northbridge used to do, managing memory, controlling high-speed I/O, are built directly onto the CPU chip itself. This gives the CPU a direct, screaming fast connection to the most important parts of the system and blows that old bottleneck away. And this is really the genius of the modern system. It gives you the best of both worlds. For a software programmer writing code, it still looks like that simple, easy-to-understand memory-mapped model. But underneath all that, the hardware is communicating over powerful, standardized physical connections, buses like PCIe for your graphics card, or USB for, well, everything else. The controller inside the CPU does all the translation. And the result? You can plug a graphics card from NVIDIA and a keyboard from Logitech into a motherboard from Asus with a CPU from Intel, and it all just works seamlessly. All right, so let's boil this all down. What are the three big things to remember from all this? First, the CPU is smart, but it's not a micromanager. It delegates tasks to specialized controllers. Second, our modern computers use this amazing hybrid system that gives us a simple software model running on top of complex but standardized hardware. And finally, this whole evolution is what saved us from the chaos of the past and gave us the plug-and-play world we all take for granted today.
But that brings us to one last kind of nagging question, doesn't it? We've established that the physical communication, the hardware bus, is all standardized now. So if the highway is the same for everybody, why does almost every new gadget you buy still need you to install its own special piece of software, its own driver, to get it to work? Well, that's a story for another time.